Okay, hello everyone, good morning. First, I will give a brief introduction. My name is Tang Qiao. I'm from a startup company. Its name is Yuan Fudao. I have been an iOS developer for more than 5 years. Some people already know me because I keep writing original iOS blog, and I have owned a WeChat official account. And also, I have written an intermediate level iOS development book. Hope everyone likes it. By the way, this book is a little bit out of date. Tang Xiaoxuan and I will update this book later this year. Hope you will like it. Before I start, I also want to say thank you to Liang Jie, the chief organizer of this conference. Thank you for inviting me. It's very great to be here. Today we are going to talk about the performance of the Swift. As we know, according to Apple's benchmark, Swift is much more faster than Objective-C. Here is the benchmark result. This slide is from Apple. The Delta Blue and Richard are two benchmark algorithms for comparing programming language speed. You can see the blue line is the Swift performance, and the green one is the Objective-C performance. So, and the value is larger, it's better. So, especially the richer benchmark, Swift is 4 times faster than Objective-C. So, obviously, Swift win this benchmark. We know Swift is a modern language, but sometimes I still think it's a little weird because during the past 20 years, Apple has the Swift Objective-C is the only programming language for macOS and iOS. So Apple has spent several decades to improve Objective-C's performance. And on the other side, Swift is a very young language. It's only 3 years old. And it's still changing very, very fast. So how can Swift beat Objective-C so badly? I think the best way to understand this thing is understand the implementation of this Swift. If we can understand the internal implementation, we can understand the performance result easily. So I think actually there are many optimization Swift has used. For example, we have compiler optimization. We know Xcode has the whole module optimization feature, which will optimize all across multiple source files. So if you have some unused protocol or any other code, the whole module optimization will delete this source code and enhance the performance. nil becomes 1 and x equals nil, there is no points at the instance anymore. So the reference count becomes 0, and the memory will be allocated and it will be marked as reusable. So it's very simple code, right? However, reference count costs a lot of CPU sometimes. I will show an example for you. Here is the example. I have an array of objects, and I want to loop this array and do some operation on each of these elements. So the best thing is Swift will add reference count increase and decrease code in this loop. So every time I loop, it will some operation to increase reference count, decrease reference count. It will cost a lot of CPU time. And actually, the reference count operation is not cheap, not simple. For strict safety, Swift need to first lock the memory and change the reference count, then unlock the memory. So it's not easy to do this operation change. But the lucky thing is Swift has value type. We have struct. Struct memory is allocated in stack, not in the heap. So the allocating is very fast. In heap, we can just adjust the heap stack pointer to allocating memory. So it's much more faster than allocating memory in heap. And struct also has no reference count anymore. So let's look at the example again. If I change the type of class from class to struct, the memory will look like this. There were no heap memory anymore, and the reference count code will be deleted because struct doesn't need any reference count anymore. So this is one important reason of why Swift is faster than Objective-C, because in your code, there is some reference count code deleted, and the memory allocating, delocating is very fast. But struct word is not perfect. I will give you a very simple an example. If one struct has many class type variables, there will be a huge problem. Let's look at this example. The struct Tangqiao, it has 3 variables. These are 3 members, and these 3 members are both class type variables. So that means if I create an instance, this struct will hold another 3 class type references. And if I assign another variable to this instance, the struct will cause 3 reference counts. 3 reference counts. So assignment will cause 3 reference count operation. So the more objects struct which the struct value has, the more reference counts there will be. So it's a huge problem if your struct contains a lot of reference members. So the reference count problem comes back in. The struct assignment will cause a lot of reference count if it contains so many class members. How to solve this problem? We need to write fast Swift code, right? We don't want this situation happens. Actually, there is a very simple solution to solve this problem. We can use a wrapper class to solve this issue. Let me show you. Here is the previous example. If we use a wrapper class to hold all the numbers, the situation will change. Here, we use a control wrapper to hold all the class members. So, if when I create X instance, the structure will only hold the wrapper, and the wrapper will hold other members. So the memory will look like this. And if I do the assignment y equals x, there will be only one reference count operation to the wrapper, and other members' reference count will stay 1. They won't be changed. So here is concluding using a wrapper class to hold class members if your struct has many class member variables. But it's a little bit ugly, right? I mean, we need to write unstraightforward code to do optimizations. So my suggestion is we should use struct members as much as possible to avoid this situation. And we can also find Apple is doing the same thing. In the Swift 2, the string, array, and the dictionary are reference types. But after Swift 3, nearly all these things are changed to the value type, including the string, array, dictionary. They are all value type in Swift 3. So because all the basic type are value type, we can much easier to avoid this situation. Then I want to discuss the second topic, the internal implementation of struct with protocol. Actually, Swift uses 2 tables to support struct with protocol, the protocol weightage table and the value weightage table. Let's know more about it. We know all the class instances are reference type, so the size of reference will always be the same as the CQ size. So if we look at the example, we have an array of drawable, and each element is class type. So every element size are the fixed because they are all pointers that have the same size, and it points to another range of memory, and then another range of memory are different size. So array elements have the same size, but this is the class type array. If we change the type of point and line from class to struct, what will happen? I mean, if we direct put them into the array, then each of the element size will be different. So that's a problem because we cannot locate every element very easily because they are different size. So if I want to get the ith element, I want to count its previous element size. After that, I can get the location of the ith element. So Apple introduced a container and the weightage table to solve this problem. Let's go through it. First, Apple introduced a container to store this type of struct. Each container has 5 words, so it's a 5-word size container. And the first 3 words are the value buffer. The value buffer is used for storing the struct type value. And the first word is the value weightage table. It's a pointer. The pointer will point at the address. It's a table. It contains the allocate, copy, destruct, and the allocate method addresses. So you use this pointer, you can find this function entry point. And the first word is the protocol weightage table. it will point at the protocol method addresses. In the example, we have a draw function, so we can use this table to find the function entry point. So this solution has an obvious problem. What if my struct is bigger than 3 words? So it cannot be put in the random buffer directly, right? There is only 3 words in the random buffer. So Apple solve this problem use a very simple way. They will, if your struct is bigger than 3 words, Apple will allocate another range of memory and put the reference of this memory into the random buffer. And if the other 2 memory of the random buffer blank, so this is Apple's solution. So in this case, the other 2 random buffer ring is unused. So let's go through an example. Here we define a function named draw or copy. To accept a draw type argument. And when I initialize the draw object, which is a point instance, and we pass this instance to this function. So this is the logic of this source code, and compiler will change this code into this. So the bottom line is the compiler generated code. The Swift compiler will create a container we just mentioned before. The container has 5 words. The first 3 words are value buffer, and the fourth word is the value weighted table, and the fifth word is protocol weighted table. So this is the container we just mentioned. And then, when I call the function, compiler will generate code to pass value to do an assignment. It will assign the value of weight and ball to the local argument. So to complete the assignment, compiler will change the argument type from the drawable to the container type. So the argument type will change. So here the argument type is changed from drawable to this container drawable type. And then it will initialize the weighted table. We can see it initializes the value weighted table, protocol weighted table as as CMC. So we have the value weighted table. With the value weighted table, we have the function entry point, the allocated copy, destruct, the allocated addresses, right? So we can use this function to help us to copy value. Also, we have the protocol weighted table. It will help us to get the draw function entry addresses. So with the value weighted table's help, we can find the allocation address and allocation function address and use it to copy value. So this time, use your value weighted table's allocation function and copy the argument value. And if the value is smaller than 3 words, it will input into the value buffer directly. So if it's a pointer is 2 word size, so it will be put into the value buffer directly. But if we change type from point to 9, it's 4 word size, so it cannot be put into the value buffer. So there will be another memory in the heap, and in the value buffer there will only be one pointer in it, point at the heap memory. So and finally, we use the protocol weighted table to find out the draw function addresses and use it to call the function. After that, we need to use the weighted table to find the destruction entry point and be allocated the memory. So this is the whole process of a value type with protocol call. So we can see Apple uses a very special container to support this operation. So later, I will use LLDB commands to inspect, to do a demo to inspect this situation in Xcode. So before that, I want to introduce some LLDB commands. Later, I will use it. The first one is breakpoint commands. It will set a breakpoint and target addresses. And the continue will continue your app to stop at your target point. It's a very simple LLDB command. And the next one is the DI commands. DI commands is used for disassemble some source code. We can use this command to inspect the weighted table we have mentioned before. We can use this to get the weighted table source code later. And the most useful command is the X command. It's used for read a range of memory. So later we'll use it to read the RDI memory. RDI is a special register. It will be the first argument when you call method. So if you call your method, you set a breakpoint and you read the RDI memory, you can get the memory layout of the argument. So the last LLDB command is the register information. We can use this command to read the register usage information. Later we'll get some useful information from this command. Okay, let's go over our demo code. It's very simple. We define a protocol. It's a drawable type, right? And we define two structs. The first one is the point struct. It has two members, so it size 2 words. And the line struct, it has 4 word size. And the initial value, well, the point initial value is 1 and 2, and the line initial value is 5, 6, 7, 8. So later we will, please remember this value, because later I will use this value to search the memory to locate this variable. So the logical code is also very simple. We create 3 instances. First one is a pointer type, second one is line type, and the third one is a drawable array. Very simple, I will say. Just like I said, I define a drawable protocol and a point to struct. It has initial value 1 and 2, and the line struct. The initial value is 5, 6, 7, 8. And our logical code is in the built-in load method. We have 3 variables. A point instance, a line instance, and a drawable array. And I set 2 breakpoints. First is an data draw function, and secondly is the output array. So I will run the demo. the time. And on the assistant editor, we can change the assistant editor type. We can see the disassemble code. So I change it. Okay. Okay, cool. Okay. So the left side is source code. The right side is the disassemble code for this source code. Actually, the source code and the assemble code is not 929 1 corresponding. So this function corresponding a range of assemble code. And after several experiments, I found the following call. This line is actually the entry point of this function call. So I need to set a point to this address. Okay, I need to put this. Okay, I need to set a breakpoint to this address. I will use. Can you see it clearly? Okay, I will set a breakpoint. Breakpoint set /a and followed by the address. Then I will use continue commands. Okay, we are at the calling address of this function. So first we need to read the RDI memory. RDI memory. We use the X command to read the RDI memory. So we get the information of this RDI. I will screenshot it and expand it. I will also use the register read command to get the register information. And I will copy this information to preview and enlarge it. Okay. This is the memory. This is the memory. We can see the first one. The first words and second words is 1 and 2 is exactly the value of the point, right? And the fourth one, as I mentioned, it should be the entry point of the value witness table. And luckily, we found this one and this one are the same. Yeah, this one is. So the LLDB gave me the information is the type meta for the point struct. So it just means it's a value witness table. And the fifth one is the same as this one. And this, LLDB tells us it's the protocol witness table. You can read this information here. It's a protocol witness table. Yeah. So it's a container struct, just like I said. And we can also use the disassemble command to disassemble this address, the fifth address, because it's the entry point of the protocol witness table. So we can disassemble it. We use these di commands to disassemble it. So we can get more information. So LLDB gave us the information. It's a protocol witness table for this point. and followed by the commands of this entry point. So it's exactly what I mentioned before. So I will continue to another point. So I continue to another breakpoint. And also we need to jump our assemble file to the following call, this place. So I will need to breakpoint set /a and followed by the address and use continue to go there. Okay. Oh, sorry. I type more continue. So we need to start. Sorry. I need to restart this app. So later, I will set breakpoint to this address and dump the memory of this array. We can inspect its memory layout. Change to disassemble. And we need to breakpoint set this address and continue. And also we need to get the memory of the RDI register. So RDI. Because it's an array, so the size will be bigger. So I will read 5 words, 15 words. So this is the memory. It's a little bit hard to read, so I also will copy this address. First, I will copy. Okay, and put it to preview, and enlarge it. So it's not easy to find the information, right? I will help you. The first 4 words are the data information for the array. So we will skip the first 4 words. We will skip, and the following 5 words are the first element of this array. So change the color. Can you find the instance of this pointer? Here, the value 1, 2 is just exactly the value of the point, right? And the 5th value is unused, so it's 0. And this value should be the value wait list table, right? And this value should be the portable wait list table. We can use disassemble command to verify it. So we remember this address. It ends with B8. I will copy this address, B8, and disassemble this address. Yes, you can see it's a meta type for the point. Can you see this information? Maybe it's a little bit. Yeah. It's type meta for this point, so it's the value wait list table, and this under with 200 should be the portable wait list table. So we can disassemble it. 200 with it. Need to 30. Oh, here. We disassemble this address. So here, LDB tells me it's the protocol wait list table for this point. So this is the first element of this array, and the second element of the array is followed. So we can get here the following 5 words here and there. different from the previous one because the 9 point is bigger. Its forward size is bigger than 3 words, so it cannot put in the value buffer. So we can only get an address, only get this address of this instance. And the followed two value buffer are 0. It's 0 and this one is 0. So this address should be the address of the 9 point. So we can read this address to verify. So this address is under with 940. We can dump this memory. 940. We can dump this memory. Use yeah. Here is the dumped memory. Can you see its value? After dump, this address, its value is 5678. It's just the exact value of this 9 point. So this is the memory layout. And also we can verify another information of this container. So the first value should be the value witness table. We can dump this address, create this place. Can use we can disassemble this code. Disassemble this code. Yeah, it tells it's the meta type for the 9. And the last one, 208. It should be the protocol witness table. 208. Disassemble it. Yeah, it tells me it's the protocol witness table for the 9 struct, right? So from the demo you can figure out how Xcode and Swift solve this problem using the container, the protocol witness table, the value buffer, and the value witness table. So it's a design internal design of Swift. Okay, let's go over today's topic. First, we have introduced a value type has better performance. Then we need to pay attention if the value type has a lot of reference count. And the extension container can be used for value type and protocol oriented programming. And we have introduced some area DB commands. It's very, very useful. It can help us to understand the implementation detail of this container. So that's my speech, and finally I want to say thank you to everyone. You know, it's not very easy to speak in English, but I think it's also not very easy for everyone here to listen pure English speech. So thank you everyone's patience. Thank you very much.